The next topic for us will be analytic issues with these designs. We want to talk about the impact of clustering in particular. In all three of the designs other than the RCT, we're going to have clustering because we're working with existing groups or clusters in the parallel and step wedge group randomized trial. And in the individually randomized group treatment trial, we create groups or clusters by virtue of the way that we're delivering the intervention. In terms of the impact of clustering on a parallel group randomized trial, the observations that we take on members of the same group or cluster will be correlated. That's our expectation before the study even starts. The members of the same group or cluster will share physical, geographic, or other connections. Those connections create a positive interclass correlation that reflects extra variation attributable to the group or cluster. You can think of it as the average pairwise correlation among any two members in the group or cluster, as shown in this definition. That positive interclass correlation reduces the variation within a group. That's a good thing. At the same time, it creates an extra component of variance, the between group piece shown here. The total variance is the sum of the two components. The intraclass correlation I defined in the previous slide as the average bivariate correlation between any two members of the same group or cluster. Another way to think about the intraclass correlation, it's the proportion of the total variation attributable to the group or cluster. Now, this particular formulation would suggest that you can only have positive values. In fact, you can have negative values. So technically the better way to think about the definition is this bivariate correlation. But since they're usually positive, thinking about it as a proportion of variance can also be helpful. If we have M members in each of G groups and we create those groups by randomly assigning participants to the groups, the variance of a group mean is as shown here. It's the usual variance of the dependent variable y divided by the number of observations contributing to the mean. You've all seen that expression, perhaps not with my notation, but you've seen that expression in every first year graduate statistics textbook. The second expression is a bit different. When group membership is not established by random assignment, for example, if we have existing groups like schools or work sites or whole communities, then the variance of the group mean has two pieces. The residual error is divided by the number of observations contributing to the mean. The group component of variance is not divided by anything. It's just sitting there. Another way to write that second expression is shown at the bottom. The variance of the group mean is the variance of the group mean from the randomized experiment multiplied by a parenthetical expression 1 plus m minus 1 times the interclass correlation. M, remember, is the number of participants in the group. The ICC is the average bivariate correlation or the proportion of variance explained by the group membership. If either M is large or the ICC is large, that parenthetical expression will be large because we're multiplying the ICC times M and then adding it to 1. As that gets to be a large quantity, you can see that we are multiplying up, increasing the variance of the group mean. And that is something that is just part and parcel of working with group randomized trials. Because groups are nested within study arms, in a parallel group randomized trial, we need to model those groups as random effects. And David Zucker published a lovely paper in 1990 showing that if you make the serious mistake of modeling those groups, nested groups, as fixed effects, you'll get an inflated type 1 error rate. So you don't want to do that. As a result of the expression that I showed you here at the bottom, the multiplication, the multiplier, the variance inflation factor, 1 plus m minus 1 times the ICC, the variance of any group level statistic is going to be larger in a parallel group randomized trial than it would have been in an RCT. The degrees of freedom available to estimate the ICC or the group level component of variance are going to be based on the number of groups and may be limited. Any analysis that ignores either the extra variation or the limited degrees of freedom is going to have an inflated type 1 error rate, and you don't want to do that. It can be serious. It could be 50%, where you want a type 1 error rate of 5%. So we have to pay attention to this. I will note that extra variation, limited degrees of freedom always reduce power. So we want to pay attention to this when we're planning the study, not just when we're analyzing the data. Let's turn now to the individually randomized group treatment trial. Observations taken on participants who receive some part of their intervention in a group or who interact with the same intervention agent, those observations will become correlated over time. And the magnitude of that correlation depends on how often they interact with each other or with the shared intervention agent, how intense those interactions are, how long those interactions last. But at the end of the day, we can expect a positive interclass correlation to develop over the course of the trial that reflects extra variation due either to the intervention agent or the small group in which participants receive some part of their intervention. At the beginning of an IRGT, the participants are independent. The observations are uncorrelated. But by the end of the study, there will be correlation in the data. The impact of the interclass correlation will depend on the nesting and membership structures that we described earlier. And this is from a recent paper by John Moyer, published in 2024. In Dr. Moyer's paper, they evaluated several analytic models for IRGT trials across all the different combinations of nesting and membership structures. For nested designs, which are the most common, the interclass correlation has a similar effect to what we observe in group randomized trials. And if you're going to protect the type 1 error rate, the analytic model needs to be matched to the membership structure. So multiple membership models if you have a multiple membership structure, single membership models if you have a single membership structure, and we should not use naive models that ignore the agents or the small groups. They will always have an inflated type 1 error rate. Remember, in IRGT trials, we can have a cross design where the same agent works in both arms, or the same agents work in both arms. That's possible if you carefully train the intervention agents and have a good quality control system to monitor to be sure that they're delivering the correct intervention to the participants that they're interacting with at a given time. And in the cross design, this is the major advantage, the interclass correlation has very little effect. And so that protects the type 1 error rate and provides flexibility in the kinds of analyses that we can do and provides much better power. I recommend the cross design for an IRGT. There is risk of contamination though. So you've got to train your intervention agents carefully and do good quality control to be sure that they're not delivering the intervention to the control participants. From both of those 2 points for nested and cross designs, you can see that it's important to document the interactions that occur between participants and these intervention agents. We encourage investigators to document which participants interact with which agents over the course of the trial and how long those interactions are. You're going to need that information at the analysis stage to account for a multiple membership model, if that's what you end up having. Less important with a single membership model. But sometimes you're not planning a multiple membership model, but you end up with one because there's turnover in staff, or some people, an agent is sick one week and another agent has to step into with their participants and deliver the intervention. So multiple memberships can occur even in an unplanned way, and you'll need to document all the interactions between participants and intervention agents in order to fit multiple membership analytic model. Strongly recommend a power analysis with realistic and data-based estimates, and you can get information on methods, analytic methods, and power methods from this paper by John Moyer. Nested designs that ignore the interclass correlation in an IRGT are at substantial risk, either being underpowered if you're going to use the correct analysis, or having an inflated type 1 error rate. The inflation is not as bad as you can have in a group randomized trial, at least for the partially nested design, but it can still be substantial, and you don't want it to be higher than 5%. The solution is to reflect the variation attributable to the small group or intervention agent in the analysis, base degrees of freedom on the number of groups or agents in arms where those exist. Here's a couple of papers by Candlish and Moyer that provide exemplary SAS code and R code for these analyses. Most investigators are not aware that IRGT trials even exist. Most of the applications submitted to NIH for funding that are proposing IRGT trials are written up as though they've got an RCT. The investigators are simply unaware that an IRGT is a possibility, not aware that they need to pay attention to shared intervention agents and group formatted intervention components. Most of the studies that use this design are unaware of it and don't use the right analytic methods and sample size methods. You've all now been warned, so please help us improve the situation here. Use the right methods when you're using those techniques for intervention delivery. What about the step wedge design? Well, we cross groups with study conditions, and that reduces the effect of the interclass correlation, just as it did in the crossed version of the IRGT. And it's the same reason. So we always have crossing in a step wedge design, so the impact of the ICC is much reduced. It's not a balanced crossing as we have in the IRGT situation, so you don't get rid of the effect of the ICC altogether, but it's much reduced. Even so, there are other potential sources of bias in the step wedge design. The intervention is confounded with time. We talked about that already. The intervention effect may vary over time. That turns out is tremendously important. We'll talk about that further. The intervention effect may vary over groups or clusters. That could also happen in a parallel group randomized trial. The patterns of correlation may vary over time. That is particularly important for step wedge designs because they are often strung out for a longer time. They last longer. There are more data collection periods. There are more opportunities for correlation to vary over time. If you assume that these biases are non-existent in your trial, you may have trouble. These threats are greater in the step wedge than in the parallel group randomized trial, and that's why I prefer the parallel version. Let's talk a little bit more about time-varying intervention effects. The traditional analysis for the step wedge group randomized trial is the Hussey and Hughes model from 2007. Virtually every application that I see coming to NIH proposing the step wedge design proposes the Hussey-Hughes analytic model. That model assumes that the intervention effect is rapid and persistent. In other words, it happens right away and it doesn't decay over time. It doesn't get stronger over time. It's a step function. It happens and it stays there. The problem is that may not be the situation in your study. The effect of the intervention may vary over time as a result, for example, of the intervention agents getting better at delivering the intervention, or it may fade over time as a result of the lack of having follow-up doses of the intervention over time. It may just fade as time goes by. Any analysis that assumes that the intervention effect is constant and happens right away could be severely biased if it turns out that the intervention effect varies over time. And we had 3 papers come out just in the last few years on exactly this issue. Kenny, Malayev, Hughes, all point to this. The intervention effect itself may be biased. It could even be going in the wrong direction. Your estimate might be going in the wrong direction. The standard errors are not correct. So all sorts of problems. You can have very inaccurate results if you assume rapid and persistent intervention effect, and it turns out that that's not the case. So I really want to caution against that. There are analytic methods that accommodate time-varying intervention effects. They're described in the 3 papers shown here, and we use them in the NIH sample size calculator for step wedge designs that we'll talk about at the end of today's lecture. We can also have treatment effect variability across groups. That can happen in the step wedge. It can happen in the parallel group randomized trial. So it's a consideration in all of these. If the effect does vary across groups, that's usually going to reduce power. And the best strategy for avoiding this is very good quality control, very good training of the people that are delivering the intervention. The correlations can be pretty complicated in the step wedge design because we've got lots of time periods, and we can have correlations between period 1 and period 3, between period 2 and period 5. So lots of different correlations. It is usually a mistake to assume that the correlation is constant over time. More appropriate is to assume that the intervention declines over time. And there are analytic methods that can deal with those things. You want to be careful not to misspecify the correlation structure. Now, with all of these problems that I've identified that we have to deal with in the analysis for group randomized trials, both parallel and step wedge and individually randomized group treatment trials, why in the world would we want to do these? Well, it turns out that they're often the best design available for the intervention that we have. And we just have to remember something that Jerry Kornfield said in a paper published in 1978. Randomization by cluster, accompanied by an analysis appropriate to randomization by individual, is an exercise in self-deception. I love the understatement. So don't do that. Pay attention to the groups and the random effect of the groups if you're using parallel or step wedge, and pay attention to the group formatted intervention components and the intervention agents if you have an individually randomized group treatment trial. I continue to say that the RCT is the best design if you can use it, if you can assure that there's no interaction among participants after randomization. The IRGT is the best alternative if you can't avoid that kind of interaction. The group randomized trial is the best if you've got an intervention that manipulates the social or physical environment or can't be delivered to individuals without substantial risk of contamination. And the step wedge design is an alternative that I consider reluctantly and encourage you to be cautious about jumping into it because it faces more risks than the parallel group randomized trial. I would argue that you can complete the parallel group randomized trial and give the intervention to the control participants faster than you can complete the step wedge design. So the argument that, oh, well, everybody gets it in a step wedge design, everybody can get it in a parallel group randomized trial design, and usually faster by simply delivering the intervention to the control participants at the end of the study. Let's talk about analytic models. So mixed models are widely used in parallel group randomized trials. If you've got 1 or 2 time intervals that are modeled in the analysis, like pretest, post-test, or you can do, let's say you've got 2 time points in the design, you could look at post-test only, you could look at post-test adjusting for baseline, or you could do repeated measures or an analysis of change scores, which is equivalent. So you've got a couple of different variations that you can use. If you fit your model using the general linear mixed model or the generalized version of that, you can't misrepresent overtime correlation because there's only one with just 2 time points. And simulations have shown that these approaches maintain the nominal type 1 error rate across a wide range of conditions common in group randomized trials. So I strongly endorse mixed model ANOVA and COVA when you've got 1 or 2 time intervals in the analysis. If you've got more than 2, it gets a little tricky. You can't use the standard repeated measures mixed model ANOVA with a compound symmetry variance covariance matrix. If you do, you're going to have an inflated type 1 error rate. There are 2 alternatives that will work just fine. One is the random coefficients model, sometimes referred to as a growth curve model. Now you're treating time as a continuous variable. You are allowing for heterogeneity in the trends that you estimate in each of the groups. and simulations have shown that this approach works quite well. The alternative is the repeated measures mixed model ANOVA, but now with an unstructured covariance matrix and with Kenward-Roger degrees of freedom. We're still modeling time as categorical, just as we did with the first option, the repeated measures ANOVA with compound symmetry. But we're using an unstructured covariance matrix and Kenward-Rogers degrees of freedom instead of compound symmetry. And simulations have shown that this approach does quite well. And it's a paper published by John Moyer, 2022. What about IRGT trials? Well, John Moyer's 2024 paper is the best one that I can point you to. He's evaluated a number of alternative analytic models for IRGTs, and for nested designs, if you've got a multiple membership structure in your data, you need to use a multiple membership model. If you've got a single membership structure, you need to use a single membership model. And you should simply not use single agent designs and naive models. Those are bad ideas. And John provides analytic code in his paper for the multiple membership model and the single membership model. So I refer you to that article. For cross designs, the interclass correlation has a negligible effect, as we noted earlier. So you've got more flexibility in analytic models. You can ignore the agents and the small groups, or you can model them. Either way, you're going to have essentially the same power, the same type 1 error rate. So it's a very good situation. You just want to take care that you avoid contamination, since that is a possibility in a cross design. What about preferred analytic models for step wedge designs? Well, there's a long series of papers going back to 2007, and I'm not going to talk about each one individually, but we've had sort of incremental improvements in the quality of the analytic models that are available. If you've got a step wedge design that's not too long and there aren't too many time periods involved, the work of Lee et al. 2021 provides a great paper on analytic methods that are appropriate. If, however, you've got a design where it goes on long enough that the intervention effect could vary over time, now you need to be looking at the 3 papers I identified earlier, Kenny et al., Malayev et al., Hughes et al., and use the methods that they present for time-varying intervention effects. Because you're at risk for that if you're following people over a longer period of time. The intervention effect has a chance to grow or fade. I'll mention cross-classification and dynamic groups. I'm not going to dwell on it. Sometimes we see these things in group randomized trials. Participants are nested within more than one non-hierarchical group or cluster. That can happen. It's not common, but it can happen. And if it does, then you have to pay attention to both kinds of groups or clusters is the solution. The dynamic groups issue, the effect of the agent or group might change over time. Careful training and standardization can avoid that. But if you think it's a possibility, there is a class of models that you can use referred to as dynamic group models. What about randomization tests? Randomization tests are an approach to analysis that don't use models at all. They're not model-based. Under the null hypothesis, the arrangement of groups in study arms is but one of many. The arrangement that we use is but one of many that are equally likely. And what the randomization test does is systematically compute the intervention effect given all possible assignments of groups to study arms. And the probability of getting a result more extreme than the one that you observed is the p-value that you're looking for. There are no distributional or other assumptions if you're not making regression adjustment for any covariates. So it's a very attractive approach. We couldn't use it for a long time because it just took too long to do the calculations. But with today's computers, it's quite easy. Mitch Gale published a paper in 1996 showing that randomization tests work very well in parallel group randomized trials. There have subsequently been papers showing how to do this in step wedge designs. So it's a quite good, perfectly good approach. I certainly can recommend it. The main weakness is that an unadjusted randomization test doesn't offer any more protection against confounding than model-based unadjusted methods. The solution is to simply incorporate regression adjustment for covariates in your randomization test. That pushes a bunch of assumptions into it, but that's the solution. Model-based methods provide parameter estimates, standard errors, and do quite well, except when you've got a very skewed or heavy-tailed distribution. So you're going to get essentially the same result with randomization tests and model-based tests usually, but if you're concerned that your outcome variable is skewed or heavy-tailed, I would point you towards randomization tests. What about something like GEE, generalized estimating equations? So GEE was developed at Hopkins by Liang and Ziegler for longitudinal data. They can be applied to parallel group randomized trials and step wedge designs, individually randomized group treatment trials. They incorporate an empirical sandwich estimator for standard errors that's asymptotically robust against getting the random effects covariance matrix wrong. The asymptotically robust is the key phrase. If the degrees of freedom for the intervention effect are much less than about 40, the empirical sandwich estimator doesn't work as it's supposed to. So you really need a large number of groups in your group randomized trial for the standard GEE to work. There are adaptations that you can use, corrections that you can use, and some of those are incorporated, for example, in SAS Procglimics. And with those, you can use GEE to analyze data for smaller group randomized trials. What about a fixed effects approach where you break the analysis into 2 stages? This is a perfectly reasonable way to go. You analyze the data to calculate group means or group slopes or group proportions, whatever the metric is that you're looking for, ignoring study arm initially, and you can make regression adjustment for covariates as you wish. And at the end of that first stage, then you've got group means or group slopes or group proportions. And in the second stage, you analyze those group means or group slopes. You can analyze them with a t-test. And this is when you compare intervention and control. And if you have balanced data, you're going to get exactly the same p-value as you would with a mixed model. These 2-stage approaches can be adapted for random coefficients model. They can be adapted for very complex designs. So a perfectly reasonable approach if you prefer it. What about deleting the unit of assignment from the model if it's not significant? Please don't do that. It's a bad idea. The degrees of freedom for this kind of test are usually very limited so that the test doesn't have much power. The standard error is not well estimated if the variance component is near 0, which is what happens when the ICC is small. So, and even if the ICC is small, if you ignore it, it can inflate the type 1 error rate. So the prudent course is to retain all random effects associated with the study design in the analysis. So don't delete the unit of assignment from the that wraps up our presentation on analytic methods, and we're going to turn next to sample size and power.